In 1979, a machine tool importer in Seattle received a shipment of 14 engine lathes from Taiwan. They were not South Bend lathes, but the bed width was identical to South Bend's. The center height was identical. The spindle nose thread was identical. The tool post standard was identical. A South Bend chuck mounted on one without modification. A South Bend faceplate fit the spindle without adaptation. Every South Bend accessory, every collet, every steady rest, every follow rest manufactured in South Bend, Indiana, bolted directly onto the Taiwanese machine as if it had been designed for it. It had been. The specifications came from South Bend's own catalog, from South Bend's own technical manuals, from a document that South Bend Lathe Works had published, revised, and distributed free of charge to every American vocational school in the country for over 70 years. A decade earlier, that same document had been cited by the U.S. Office of Education as the finest piece of machine tool training literature produced by any American manufacturer. It was called How to Run a Lathe. South Bend had published it first in 1906. By 1979, it had sold over 1 million copies. It was at that moment the most widely distributed machine tool training manual in the history of American manufacturing. It was also by then the engineering specification for the machine that was replacing South Bend in every American job shop that could not afford to wait. But the real story of South Bend Lathe is not the manual. It is the story of the machine that turned a generation of Americans into machinists, and what happened to the company when that generation's children stopped needing to learn the trade the same way. Every week on this channel, we tell the stories of the American companies that built the machines the factory ran on, and what the market did to them. Like this video and subscribe if that history matters to you. This story begins not in Japan and not in Taiwan, but in South Bend, Indiana, in 1906. South Bend, Indiana in 1906 was not a quiet town. It sat at the industrial crossroads of the American Midwest, 4 hours by rail from Chicago, 3 hours from Detroit, positioned inside the manufacturing corridor that was becoming the productive engine of the American economy. The Studebaker Brothers Manufacturing Company was already there, building wagons and early automobiles on the west side of the St. Joseph River. Oliver Chilled Plow Works was there. Dodge Manufacturing was there. The city had rail connections, a skilled immigrant labor pool, and the kind of commercial density that made it possible to buy a precision ground casting on a Tuesday and have it machined and assembled by Friday. Into that environment, two brothers named John H. Beaudry and Samuel R. Beaudry established South Bend Lathe Works at 400 West Sample Street, a 2-story brick building on the near north side of the city, close enough to the rail yard that raw steel stock could be delivered to the loading dock and finished machines could be crated and shipped within the same week. What they had identified was a gap. The American machine tool market of 1906 was divided against itself. At the top end sat the precision tool room lathe, the kind of machine that a skilled tool and die maker used to produce punches, dies, and gauges, held to tolerances measured in 10,000ths of an inch. Manufacturers like Hendy and Lodge and Shipley served that market at prices that a small job shop could not justify. At the other end sat the heavy production lathe, the machine bolted to the floor of an automobile plant or a foundry, running the same cut 8 hours a day, built for volume and durability rather than versatility or precision. Between those two extremes sat the American job shop, the small machine shop that repaired equipment, produced replacement parts, took contract work from larger manufacturers, and trained its own machinists by putting an apprentice next to a machine and telling him to make it run. That shop needed a lathe that was accurate enough to hold a tolerance, versatile enough to thread, taper, and face a wide variety of work, and priced low enough that a shop owner running 3 or 4 machines could justify the purchase without a government contract to back it up. The Beaudrys built that lathe. The South Bend 9-inch engine lathe, named for its swing, the maximum diameter of workpiece the machine could rotate over its bed, entered production around 1906 and reached its mature commercial form within the first decade. The bed was available in multiple lengths, from 36 inches to 54 inches between centers, accommodating the range of work a job shop encountered on any given week. The spindle ran in precision bronze bearings, ground to a run-out standard that competing machines at the same price point did not consistently achieve. The list price on the basic 9-inch configuration ran approximately $45 to $65 in the years before the First World War, equivalent to roughly $1,400 to $2,000 in today's money. A figure that placed it within reach of a working machinist who wanted his own equipment and well within the purchasing authority of a vocational school that needed to equip a shop class. That last point mattered more than the Baudrys may have anticipated. In 1917, the United States Congress passed the Smith-Hughes National Vocational Education Act, the first federal law to fund vocational training in American public schools. The act created a direct funding stream for shop programs, home economics, and agricultural instruction across every state in the Union. For machine tool builders, the Smith-Hughes Act was not just educational policy. It was a procurement opportunity of the first order, a federally funded expansion of school machine shops, operating on a standardized curriculum, purchasing equipment through a coordinated channel, and needing a lathe that was affordable, durable, teachable, and supported by training materials that a shop teacher with 2 years of trade experience could actually use. Southbend had the lathe. Southbend had the manual. Southbend had the price. The U.S. Office of Education began directing Smith-Hughes funding towards South Bend Lathes within the first years of the program's operation. By the mid-1920s, South Bend Lathe Works had secured what no amount of advertising in American Machinist magazine could have purchased outright: a position as the de facto standard machine tool of the American vocational education system. At peak employment through the 1940s and into the 1950s, South Bend Lathe Works employed approximately 1,500 workers at the Sample Street facility. It was shipping lathes to school systems from Maine to California, to job shops from the Great Lakes to the Gulf Coast, and to military training installations that needed a machine a recruit could learn on in 6 weeks and run reliably for the duration of a war. That position had taken 20 years to build. It would take 20 more to understand what it was worth, and another 20 after that to watch it come apart. Walk into an American vocational school machine shop in 1955 and you would find it before you saw it. The sound came first, a low, steady hum from the spindle motor, the kind of mechanical certainty that a well-maintained lathe produces when everything is correctly aligned and correctly loaded. Then the smell, whey oil on precision ground cast iron, cutting fluid misting off a workpiece rotating at 300 revolutions per minute, the faint metallic sharpness of fresh chip stock curling off a high-speed steel tool bit. Then, as your eyes adjusted to the fluorescent light and the gray industrial paint of the shop walls, you would see the row of them. South Bend 9-inch engine lathes bolted to the concrete floor in 2 facing rows, each one attended by a student who was learning at that moment what it meant to make a dimension repeatable. The South Bend 9-inch was not a large machine. It weighed approximately 500 pounds in its standard bench configuration, light enough that 2 men could position it, heavy enough that it did not move under cut. The bed was a single casting of close-grained gray iron, ground flat on its upper ways to a tolerance that South Bend's quality control department verified with a precision straight edge before the machine left the plant. The headstock, the fixed end of the machine that housed the spindle and the drive gearing, was integral to the bed casting, not bolted on as a separate assembly. That single-piece construction was not an accident. It was the reason the machine held its alignment decade after decade in conditions that would have shifted a lesser design out of tolerance within the first year. The spindle itself ran in precision bronze sleeve bearings, adjusted by the factory to a radial runout, the amount the spindle center wandered from true as it rotated, of less than 1/1000th of an inch. In practical terms, that meant a skilled operator could turn a 2-inch diameter steel shaft to a diameter accurate within 0.5 without any additional measurement beyond the machine's own graduated dials. For a job shop producing replacement parts, that was not a luxury. It was the minimum standard the work required. 2 mechanical features separated the South Bend from cheaper competitors at the same price point. The first was the quick change gearbox, a selectable gear train controlled by 2 levers on the front of the headstock that set the feed rate and thread pitch for the carriage without requiring the operator to remove and reinstall change gears by hand. Threading a workpiece on a machine without a quick change gearbox meant calculating the correct gear combination, pulling the change gears from a storage rack, mounting them on the stud and idler posts in the correct sequence, and verifying the mesh before cutting the first thread. On a South Bend, the operator consulted the thread chart mounted on the gearbox cover, moved 2 levers to the indicated positions, and engaged the half nut. The setup that took 20 minutes on a lesser machine took 2 minutes on the South Bend. In a school shop running 30 students through a threading exercise in a single class period, that difference was not trivial. The second feature was the back gear, a secondary gear reduction engaged by a pin through the headstock casting that reduced spindle speed to a fraction of its direct drive rate for heavy cuts and coarse threading. Engaging the back gear on a South Bend produced a sound that every machinist who learned on one remembers without being asked to. A solid, deliberate mechanical engagement, not a grind, not a rattle, but a firm seating of gear teeth that told the operator, without looking, that the reduction was fully engaged and the machine was ready for the work. At a list price of approximately $485 for the standard 13-inch heavy-duty model in 1940, equivalent to roughly $10,300 in today's money, the South Bend sat well below the Monarch 10E toolroom lathe at $2,200 and modestly below the LeBlond Regal production lathe at $650. It occupied the precise center of the American lathe market, more capable than a production machine, more affordable than a toolroom machine, and better documented than either. That documentation was not incidental. It was structural. How to Run a Lathe, first published in 1906, revised continuously through 6 decades, was not a brochure. It was a 150-page technical manual covering machine setup, tooling geometry, cutting speeds, feed rates, threading calculations, taper turning, and work holding. It was written in plain American English, illustrated with dimensioned drawings, and organized so that a shop teacher with 2 years of trade experience could use it as a complete curriculum. South Bend distributed it free of charge with every machine sold to a school program and sold it through dealers at cost to commercial buyers. By 1945, it had gone through more than 30 print runs. By 1960, it had sold over 1 million copies. No other American machine tool builder had produced anything like it. The U.S. Navy standardized South Bend lathes for its shipyard apprenticeship programs at Norfolk, Bremerton, and Philadelphia. The U.S. Army Ordnance Corps equipped its field maintenance training installations with South Bend 9-inch and 13-inch models throughout the Second World War. The War Production Board's Vocational Training for War Production Workers program, the emergency initiative that trained over 3 million defense workers between 1940 and 1945, designated South Bend as a primary supplier for its machine shop training centers. The National Education Association cited How to Run a Lathe as recommended instructional material for secondary vocational programs. The American Vocational Association, the professional organization of shop teachers nationwide, treated South Bend as the default equipment specification for any school building a machine shop from scratch. The nameplate on the headstock was not a city of origin. It was a curriculum standard. By 1942, the United States was running a war on 2 oceans simultaneously, and the American factory floor was the weapon. The War Production Board had calculated in the first weeks after Pearl Harbor that the Allied victory plan required a specific number of aircraft engines, tank turret rings, naval gun mounts, and artillery shell casings to be produced per month, and that the machines capable of producing them to the required tolerances were in several critical categories in short supply. The solution was not to build more factories. There was not time. The solution was to train more machinists, quickly, in temporary facilities on machines that a recruit with no prior manufacturing experience could learn to operate to production standard within 6 weeks. South Bend Lathe Works received its War Production Board priority designation in early 1942. The designation meant 2 things. South Bend would receive steel allocation ahead of civilian production priorities, and South Bend machines would be directed to the Vocational Training for War Production Workers program's 800-plus training centers operating across the country. A typical center, occupying a converted warehouse or a school building with its gymnasium floor reinforced to bear the load, ran 3 shifts per day, 6 days per week, cycling 40 students per shift through a compressed curriculum built around the South Bend machine and the South Bend manual. Training Center Number 7 in Dayton, Ohio, ran that schedule from March 1942 through August 1945. Its 12 South Bend lathes, 9-inch and 13-inch models in equal proportion, produced over that period not finished parts but finished machinists, men and women who arrived without knowledge of a micrometer and left capable of turning a shaft to a diameter accurate within 1/1000th of an inch, threading it to a standard pitch, and fitting it to a mating part that had been produced on a different machine in a different city to the same specification. The South Bend Lathe in Training Center Number 7 in Dayton, Ohio in the winter of 1943 turned out the machinist who turned out the part that kept the bomber flying. The tolerance on that part was held to 1,000th. The machine that held it was built 4 hours north in South Bend, Indiana. That was the moment. Not a single contract, not a single product launch, not a single trade show demonstration. The moment was 10,000 of those moments, running simultaneously in converted warehouses and school gymnasiums from Portland, Maine to Portland, Oregon, on machines that cost $485 and weighed 500 pounds and held their alignment through 3 shifts a day because the casting had been done correctly and the ways had been ground correctly and the spindle bearings had been adjusted correctly before the machine left the Sample Street plant. The U.S. Navy's shipyard apprenticeship programs at Norfolk Naval Shipyard, Puget Sound Naval Shipyard in Bremerton, Washington, and Philadelphia. Naval Shipyard each standardized on South Bend lathes for their first-year machinist training sequences. A naval apprentice who completed the South Bend curriculum at Norfolk could be transferred to Bremerton and sit down at an identical machine on his first day without reorientation. The standardization was not bureaucratic convenience. It was operational necessity, the kind of interchangeability that the American manufacturing system had been building toward since Eli Whitney's Armory, now applied to the men who ran the machines as well as the parts the machines produced. The U.S. Army Ordnance Corps equipped its field maintenance training installations at Aberdeen Proving Ground in Maryland and at the Ordnance School at Fort Lee, Virginia with South Bend lathes throughout the war years. An Ordnance Corps machinist trained on a South Bend could maintain the precision components of artillery breech mechanisms, tank transmission shafts, and small arms components in forward repair facilities. Work that required holding tolerances on worn and damaged parts that no blueprint had anticipated, using skills built on a machine that had taught those skills without shortcuts. The war ended in August 1945. The machines did not stop. The 3 million defense workers trained between 1940 and 1945 did not all return to their previous occupations. A significant portion of them, men who had learned to run a lathe in a converted warehouse in Dayton or Detroit or Tacoma, took that skill into the post-war American economy and built careers on it. They opened job shops. They took positions in the expanding automotive supplier base. They staffed the machine rooms of municipal utilities, railroad maintenance facilities, and agricultural equipment dealerships across the country. They bought their own South Bend lathes through the dealer network, set them up in garages and small commercial spaces, and ran them for the next 30 years, producing work that the American industrial economy needed done. South Bend's dealer network at its post-war peak numbered more than 500 independent machine tool distributors operating across all 48 states. Each dealer maintained a demonstration floor, a parts inventory, and, critically, an application engineer, a trained machinist who could visit a customer's shop, evaluate the work being produced, recommend tooling and set up modifications, and solve the problems that arose when a new operator encountered a new material or a new part geometry for the first time. That application engineering service was not a selling feature. It was the reason a job shop owner called his South Bend dealer before he called anyone else. The accessory ecosystem that South Bend had built around the 9-inch and 13-inch lathes reinforced that loyalty at every transaction. South Bend manufactured its own chucks, its own colettes, its own steady rests and follow rests, its own taper attachments and milling attachments and tool post grinder attachments. Every accessory was designed and dimensioned to the South Bend spindle standard, a standard that, by 1955, had been in continuous production for nearly 50 years and was installed in machine shops and school programs from one coast to the other. A shop that had standardized on South Bend did not simply prefer South Bend. It had made a capital investment in a system of tooling and fixturing that was dimensionally committed to the South Bend standard. Switching to a competitor meant not just buying a new lathe. It meant buying a new chuck, new collets, new tooling blocks, new everything. That lock-in was not predatory. It was the natural consequence of building a good machine and supporting it completely for half a century. By the mid-1960s, How to Run a Lathe had gone through more than 40 print runs and sold over 1.5 million copies, making it, by any reasonable measure, the best-selling machine tool manual in the history of American manufacturing. It was used as a primary text in secondary vocational programs in all 50 states. It was cited in the curriculum guidelines of the American Vocational Association. It was stocked in the reference sections of public libraries in manufacturing cities from Rockford, Illinois to Spartanburg, South Carolina. A copy came with every South Bend lathe sold to a school program and could be ordered through any dealer for $25. In the back corner of a high school machine shop in Elkhart, Indiana, in the fall of 1967, a 16-year-old student stood at a South Bend 9-inch lathe for the first time. His shop teacher, a former Navy machinist who had learned the trade at Puget Sound Naval Shipyard on a South Bend during the war, placed a copy of How to Run a Lathe on the shelf above the machine and told him to read the first 3 chapters before touching the controls. He read them. He touched the controls. He engaged the back gear for the first time. That solid, deliberate clunk of gear teeth seating under load, and felt through the headstock casting and into the concrete floor, the machine come alive under its own mechanical authority. He did not know, standing there in 1967, that the machine he was learning on would outlast the company that built it by more than 4 decades. He did not know that the manual on the shelf above him would still be in print 60 years later, republished by a third party because the knowledge in it had not become obsolete, even though the company that wrote it had ceased to exist. He did not know any of that. He was learning to cut a thread. The South Bend was teaching him. The first warning arrived not as a crisis, but as a line item. In 1968, the National Machine Tool Builders Association published its annual statistical report on American machine tool production and imports. Japanese imports had been tracked as a separate category since 1965, a concession to the fact that the numbers had become too significant to fold into the general foreign import column without distorting the picture. In 1965, Japanese machine tool imports represented 8% of the American market by value. In 1968, that figure was 14%. In 1972, it crossed 19%. South Bend's management read those numbers. What they did with them is the central question of the company's final chapter. The answer, as best the historical record indicates, was very little, because South Bend's management was no longer by that point a machine tool company's management. In the mid-1960s, South Bend Lathe Works had been acquired by Miles Laboratories of Elkhart, Indiana. Miles Laboratories was the company that made Alka-Seltzer. It made Flintstones vitamins. It was a consumer products company whose core competencies were pharmaceutical formulation and mass-market advertising, disciplines that had no structural connection to the engineering investment required to keep a precision machine tool line competitive in a market undergoing fundamental technological disruption. Under Miles Laboratories' ownership, South Bend's engineering budget was held flat. The 9-inch and 13-inch lathe designs, which had reached their mature mechanical form in the late 1940s and early 1950s, were not substantially revised. The quick-change gearbox, the back gear system, the spindle bearing design, all of it remained essentially unchanged from the Eisenhower administration through the Nixon administration, while the global machine tool market was transforming around it at a pace that no amount of brand loyalty could permanently insulate against. The transformation had a specific shape and a specific name. Numerical control, NC, had been demonstrated at the Massachusetts Institute of Technology in 1952, funded by the U.S. Air Force as a solution to the problem of producing complex aircraft structural components to tolerances that manual machining could not consistently achieve. By the early 1960s, NC machine tools were entering American production plants. By the late 1960s, Computer Numerical Control, CNC, had replaced the punched paper tape of early NC systems with a dedicated microprocessor that stored programs internally, allowed editing at the machine, and could execute complex machining sequences automatically. A CNC turning center, a lathe controlled by a computer rather than by a machinist's hands, could run a complete part cycle, change its own tooling, measure the finished dimension, and adjust its next cut accordingly, unattended, at a rate that no manually operated lathe could match on production volume. South Bend had no answer for this, not because the engineering was beyond reach, but because the ownership structure had eliminated the engineering investment that an answer would have required. A consumer products conglomerate that had purchased a machine tool company for its asset value and its brand recognition was not positioned to fund the $8 to $12 million CNC development program that surviving in the 1970s machine tool market would have demanded. The vocational school market, South Bend's institutional foundation, was eroding simultaneously from a different direction. The Education Amendments of 1973 restructured federal vocational funding away from the dedicated shop program grants that the Smith-Hughes Act framework had provided since 1917. School districts facing budget pressure began closing machine shop programs that required expensive equipment, specialized teachers, and dedicated floor space. Between 1973 and 1983, enrollment in secondary machine shop programs across the United States fell by more than 60%. The institutional buyer that had anchored South Bend's order book for 50 years was contracting, not because the machines were inadequate, but because the programs that used them were being defunded one school district at a time. South Bend was losing its two markets simultaneously, and its owner was thinking about vitamins. In 1977, Jet Equipment and Tools of Tacoma, Washington began importing the Jet 9-inch bench lathe from a Taiwanese manufacturer whose name did not appear in the Thomas Register of American Manufacturers because it was not an American manufacturer. The Jet lathe's list price was $395. The South Bend 9-inch list price was $890. The Jet lathe's bed width was identical to South Bend's. Its center height was identical. Its spindle nose thread was identical. A South Bend chuck mounted on it without modification. A South Bend steady rest fitted its bed without adaptation. The Taiwanese manufacturer had taken South Bend's published catalog dimensions, freely available in every vocational school technical library in the country, reproduced in How to Run a Lathe in sufficient detail to constitute a dimensional specification, and built a machine around them, not a copy in the counterfeit sense. A machine built to the same standard from cheaper materials with less precise finishing at half the price. The job shop owner who had bought South Bend for 30 years looked at the Jet lathe in his dealer's showroom. He put a South Bend chuck on the Jet spindle. It fit. He ran the carriage down the bed. It moved without binding. He checked the spindle with a test indicator. The runout was not what a South Bend would show, but it was adequate for the work his apprentice would be doing on a second machine. He bought the Jet. That transaction, repeated in machine tool dealerships across the country through the late 1970s and into the 1980s, was not a betrayal of American manufacturing. It was a rational economic decision made by a small business owner operating on margins that left no room for brand loyalty at twice the price. The Jet was adequate. Adequate was enough. The second blow came from a different direction entirely. In 1978, Mori Seiki of Nagoya, Japan introduced the SL1 CNC turning center to the American market through its North American distribution network. The SL1 was not competing with the South Bend 9-inch. It was competing with the idea that a manually operated lathe belonged in a production environment at all. The SL1 ran unattended. It changed its own tools from a 12-position turret. It measured finished diameters with an in-process gauging system and adjusted its next cut without operator intervention. Its list price through American distribution was approximately $42,000, 47 times the price of the Jet lathe, and nearly 50 times the price at which South Bend was trying to hold its production lathe market together. South Bend had nothing in that category. No CNC product, no development program, no engineering staff positioned to produce one. Amstead Industries, which had acquired South Bend from Miles Laboratories in 1979, inherited a company whose product line had not been substantially revised in 25 years and whose two core markets, vocational education and small job shop production, were both in structural decline. The decisions that followed were not complicated. They were just final. Production at the Sample Street plant in South Bend, Indiana, was wound down through 1980 and into 1981. The workforce that had peaked at approximately 1,500 employees in the post-war years had already contracted to fewer than 400 by the time Amstead completed the acquisition. By the time the last South Bend lathe rolled off the assembly line in the fall of 1981, that number was smaller still. A skeleton crew completing the final production run of a machine that had been in continuous manufacture for 75 years. The dealer network collapsed within 4 years. 500 independent machine tool distributors who had built their businesses around the South Bend line found themselves holding parts inventory for a machine no longer in production and representing a brand no longer able to deliver new equipment. The application engineers, the trained machinists who had been the human infrastructure of South Bend's customer relationship, dispersed into other trades or retired without successors. The The spare parts supply chain fragmented. Aftermarket suppliers in Taiwan filled the gap with replacement KT components dimensioned to the South Bend standard, because the South Bend standard was still the standard that half the used lathes in American job shops were built to. The irony was exact and total. The Taiwanese parts industry that had helped displace South Bend now sustained the machines South Bend could no longer support. The plant went quiet. Indiana stayed. The machines did not disappear, they redistributed. When the Sample Street plant closed and the dealer network dissolved, the existing inventory of South Bend lathes, tens of thousands of machines installed in job shops, school programs, and small manufacturing facilities across the country, did not go to the scrapyard. They went to the used equipment market, to estate sales, to plant liquidation auctions where a South Bend 9-inch in running condition sold for $200 to $400 in 1983, and nobody thought much about it either way. 40 years later, that same machine sells for $800 to $20,500 on eBay, and it sells within days. The Taiwanese clone that replaced it in the American dealer showroom sells new for $600 to $1,200. The original, used after 6 decades of service, commands a premium over its replacement. That is not sentimentality. That is the used machine market performing its most precise function, pricing the difference between a casting that was done correctly and a casting that was done adequately, between a spindle bearing that was adjusted by hand at the factory and a spindle bearing that was set by a fixture and left. A South Bend 9-inch lathe built in 1962 and properly maintained will hold a spindle runout of less than half a thousandth of an inch in 2026. The machinist who buys one on eBay for $1,800 knows that. The price reflects it. The community that sustains these machines is specific and active. On the Practical Machinist forum at practicalmachinist.com, the online gathering place of American machinists, toolmakers, and machine tool collectors, the South Bend Thread Archive runs to more than 600 pages of accumulated diagnosis, restoration guidance, part sourcing, and technical discussion. A machinist in rural Kansas posts a photograph of a South Bend 9-inch he pulled from a barn, asking about spindle bearing clearance. Within 24 hours, 3 members have responded with the factory specification, 2 have identified aftermarket bearing sources, and 1 has uploaded a scan of the relevant page from the original South Bend service manual. The knowledge did not disappear with the company. It migrated to the community that valued it. The Vintage Machinery website at vintagemachinery.org maintains the most complete digital archive of South Bend catalogs, service manuals, and parts lists available anywhere, covering production years from 1910 through 1979, accessible without charge to anyone with an internet connection. It is used by restoration hobbyists, by community college machine shop instructors sourcing parts for school equipment, and by professional rebuilders who are returning worn South Bend machines to original factory specification using hand-scraping techniques that have not changed since the machines were new. Those rebuilders are rare. The craft of waste scraping, the process of restoring a machine tool's precision surfaces by hand, using a hardened steel scraper and a precision reference surface to remove high spots measured in millionths of an inch, requires years of training and a tactile sensitivity that cannot be taught from a manual alone. The machine tool rebuilder who could take a worn South Bend with 1.5 thou of bedware and return it to factory tolerance in 2 weeks of bench work was an American professional category with a multi-year apprenticeship, a professional association, and a 40-year career. When the South Bend market collapsed, the economic base that had sustained that profession collapsed with it. The rebuilders who were working in 1981 retired. The apprentices who would have replaced them were never trained. The work itself did not disappear. The people who could do it did. The surprise is what survived in a form nobody anticipated. How to Run a Lathe, first published by South Bend Lathe Works in 1906, continuously revised through the 1960s, the best-selling machine tool manual in the history of American manufacturing, is still in print in 2026. Not published by South Bend Lathe Works, which no longer exists, published by independent reprint houses working from the public domain editions, sold through Amazon and through used bookshops and through the online stores of machine tool collectors who stock it alongside vintage South Bend chucks and original factory literature. A first edition in good condition sells for $45 to $90. A clean 1960s revision sells for $12 to $18 new from a reprint supplier. and the dimensional standard that Southbend established in 1906. The bed width, the center height, the spindle nose thread of the 9-inch engine lathe is still the standard that Taiwanese, Chinese, and Indian manufacturers build their small bench lathes to in 2026, so that their accessories are compatible with the Southbend machines still running in American garages and small shops. Southbend set the standard. Southbend disappeared. The standard remained, carried forward by the industry that displaced it, because the standard was too useful to abandon even after the company that created it was gone. The ghost of South Bend Lathe Works is still running in American shops. It just doesn't say South Bend on the nameplate anymore. In the back of a machine shop in Elkhart, Indiana, 12 miles from where Miles Laboratories once signed the acquisition papers, there is a South Bend 9-inch lathe, serial number 2041847, built in 1962. The spindle still runs true, the chuck still holds, the compound rest still feeds at the rate the operator sets it. The nameplate still reads South Bend, Indiana. The company that stamped it there stopped making lathes 43 years ago. The lathe has not noticed. We tell these stories because the machines remember what the market forgot. That American manufacturing was not just an economic category. It was a body of knowledge built over generations, held in the hands of people who knew what a correct cut sounded like and what a worn spindle felt like, and what it meant to hold a dimension that a blueprint required and a part depended on. Southbend Lathe Works taught that knowledge to more Americans than any other machine tool builder in the history of this country. It taught it in school shops and in naval shipyards and in wartime training centers and in the garages of men who wanted to make things correctly and needed a machine that would help them do it. The company is gone. The knowledge is not. Subscribe to keep hearing where it came from.